All right, moving on. Probably the last video here for section 2. We're going to look at the generic form of the elimination method and then one more example. So what we want to do is we want to think about our operators as just these L's. So L sub 1 operating on X plus L sub 2 operating on Y is equal to that function F1. And then my second equation, very similar. I don't know if I can get my computer to go. L sub 3 operating on X plus L sub 4 operating on Y. That'll be equal to F sub 2. So here's our second equation. All right, so if we want to use that elimination method, then just a quick shorthand way of doing it, we can get rid of, let's say we want to get rid of the Y first, and to get rid of the Y and only have X's left over, you can just kind of simplify it down to be this. So let me write it out and then I'll explain it a little bit. Okay, so what we're doing here is that we are multiplying the top equation by L4, and we're multiplying the bottom equation by negative L2. Then if we add the two equations together, we're just crossing out the y's. Because we multiplied the top equation by L4, we're going to have L1, L4 on the x. We multiplied the bottom equation by negative L2, so we're going to have negative L2, L3 on the x. And when we add those two things together, we get this operator added onto the x. Now this g on the other side, this g is what we get when we operate on F1 by L4 minus operating L2 on F2. So just to kind of write out what that would be, let's see, it would be L4 operating on F1 minus L2 operating on F2. So that's what that g is on the right-hand side after you add the two equations together. All right, so given that, we can kind of write out some steps. So here are the steps to the elimination method. So make sure the system is first written in operator form. You'll hardly ever be given operator form. You'll just be given the regular algebraic way of writing these things out. So change it to operator form. Once you have it in operator form, this is where you want to eliminate one of the variables. If the system is what we call degenerate, so degenerate just means that the two equations that you're given are different. So if you remember back from algebra, sometimes you were given two equations that had an infinite number of solutions. That's because they were the same line, or they had no solutions because they were parallel lines. So for us, for differential equations, degenerate just means that the two equations that you're given are different from one another so that they don't generate the same solutions, basically. Just know that everything you're going to be given is degenerate in this case. So if the system is degenerate, then we're going to be using that thing that we just wrote down above here, this. Let me just copy it. Okay. All right. So, if possible, the next thing that you want to do is you want to use the system to derive an equation that involves just x of t or y of t. So this may not be possible based on your question, but when you do this process to eliminate the x or vice versa, a very similar way of eliminating the y, sometimes you're still going to have some strange things where you can't isolate the x or isolate the y, but just hope that that works out. We'll talk about what to do if it doesn't work out in the future. Okay, so if possible, use the system to derive an equation that involves just x or y, but not its derivatives. Then you're going to substitute into the other equation. Okay, next thing that you want to do is you want to eliminate the x or the y and solve for the other. And then finally, remove the extra constants by substitution. Okay, so now that we have this written down, let's go through one more example of solving one of these, and then we'll move on to section 3. All right, so here's our system. x double prime of y plus y prime. Well, let me get rid of the t's here. So just x double prime plus y prime minus x plus y is equal to -1. And then we're also going to have the other equation, x prime plus y prime minus x is equal to t squared. Okay. We do have a second order derivative up here, but just know that this process works for these as well. So first thing that you want to do, step one, is you want to rewrite your differential equations. They're already in the right format. Basically, this x we would need to move over. You can just kind of do that in your heads, and then you want to move these x's and these y's together. But we're going to rewrite this using those operators. So let's look at the first equation and my x's. I have a second derivative on this x, and then this is just going to be a -1 here, so we could rewrite that as d squared minus 1 operating on x for the first equation. As far as the y's go, I have a single derivative on y plus a 1 operating on y, and that's all equal to -1 on the right-hand side. For my second equation, as far as the x's are concerned, I have a first derivative x minus a 1x, so d minus 1 acting on x, plus I have just the single derivative on y, so just d acting on y, and that's going to be equal to t squared on the right-hand side. You don't have to do this next step, but just so you can kind of visualize it a little bit, we could write out what my L operators are from the generic format up top. So L1, that's going to be the d squared minus 1. L sub 2 is going to be d plus 1. L sub 3 is d minus 1. And then L sub 4 is just going to be the operator d. Okay. You could either at this point memorize a way, so this would be the way of eliminating the y to only have x left over, and then a very similar one for eliminating the x to have just y's left over. But I hope you can just kind of see what to do at this point. So just looking at it, let's see what I did in my notes here. So the way that I did it is, I just used this thing up top here, the L1, L4 minus L2, L3 thing. So basically what I'm going to do is I'm going to multiply by d plus 1 on the bottom, and then I'm going to multiply by d up top. Oh, that should be a negative, sorry. We're going to multiply by a positive d on the first equation, negative parentheses d plus 1 onto the second equation. So just to kind of write it all out, it's going to be this. Another way to do it is just to copy the equation here. So we're going to have L1, L4 minus L2, L3 operating on x, and that's equal to g. But remember, g is a little special thing happening with these f's over here. But let's just write out what it's going to be. So we're still going to have that d squared minus 1. This is from the first equation here. So that's my L1, and that's going to be times my L4, which is d. All right, minus, then it's going to be the L3 there, or sorry, the L2, d plus 1, times the L3, the d minus 1. I'm going to put all of these in its own parentheses. Oh, geez, sorry. Because remember, this is now its own new operator, and this is going to be acting on x itself, and I'm going to have that g on the other side, where g is going to be L4d acting on the function -1 minus L2, L2, which is d plus 1. That's going to be acting on the function t squared. Okay, so if you like just writing the formulas down and plugging stuff into the formulas, that's fine and it's okay. It's just that you have a lot to remember. I always think it's easier just to look at the two equations that you have and generate it yourself. So we multiply the top equation by d. We multiply the bottom equation by negative d plus 1. The y's are being eliminated. We're going to have the d squared minus 1 times d minus, we're going to have the negative d plus 1 on the d minus 1. That whole thing is being operated on just x after you add the two equations together. On the right-hand side, we're going to have d operating on this function -1, and then negative d plus 1 operating on the function t squared. So let's simplify this down, and it will simplify down not horribly. So I simplified it down like this. This is also the way that the book did it here. So we still have that d squared minus 1, but this is just going to be a d minus 1 coming out front here. And this is operating on x. That's going to be equal to the right-hand side. D of negative 1 is just 0. That's the derivative of negative 1. But over here, we're going to have negative derivative of t squared. So that's negative 2t. And then negative just 1 times t squared, which is t squared. So it may be kind of hard to see why this operator changes into this, but just do the algebra. If you really have to, multiply all this stuff out and then factor it back to be this. But another way of thinking about it is that when you multiply these two things together, it gives you a d squared minus 1. So now both of these terms have a d squared minus 1 that you factor out, and then you're left with this d, and then this is going to end up being a negative 1 here. So just take the time and do the algebra to get from here to here. It's not too hard. All right, but now that we're here, we're going to think about this as if it's its own differential equation. Which means this does have a triple derivative in there of x, but remember you can still do auxiliary stuff, even for triple derivative stuff, a third order differential equation. So now we're going to solve this as is, which means doing the auxiliary to get the homogeneous solution, and then we're going to find the particular solution using the undetermined coefficients thing. Let me come down to the next page here. So for the auxiliary equation, that's going to be looking at r squared minus 1 times r plus 1, and that's equal to 0. All right, so this auxiliary is just coming from the differential equation up top here. The second derivative on x, that's the r squared minus the 1. All right, so I cut myself out there, but sorry about that. I hit the wrong button, and then I goofed up my stuff a little bit. So let me just fix what I had unfixed earlier. So we're here. I know I just kind of stopped the video and restarted it, but I'll explain what I did. So this should factor into d squared minus 1 times d plus 1. Okay, cool. And so then when you get your auxiliary equation, you're down here, r squared minus 1 times r plus 1 is equal to 0. And then from there, you're going to get your auxiliary roots. So you're going to have r is equal to plus and minus 1. We just have to be a little bit careful here because 1 is a double root. All right, so I goofed this up a little bit, but I hope you just kind of go on your own and fix it. So when you multiply this all out and factor it, this would factor out into d squared minus 1 times d plus 1. Changing that into the auxiliary equation, you're going to have r squared minus 1 times r plus 1 is equal to 0. This is the solution then to those auxiliary equations, plus and minus 1, where 1 is going to be a double root and negative 1 is just a single root. So when we write out the homogeneous solution, we're going to have c1 e to the 1 plus c2. Because 1 is a double root, we are going to have to include a term that has a t out in front. So c2t to the e to the t, and then we're going to have c3. And this is the negative 1 root, so that's just going to have a negative t up top here. All right, so we did look at a couple examples of these with the triple derivatives or the third order differential equations and using the auxiliary root to solve them. It's the same process as we did for the second order stuff. So the homogeneous solution, c1 e to the t plus c2 t e to the t plus c3 e to the negative t based on my roots of 1 and negative 1, where 1 is a double root. All right, after the homogeneous stuff, we have to find the particular solution. The particular solution we're going to get using the undetermined coefficients method. Okay. To do this part, we have to look back at the original equation we have, which is here. So we have this third order thing is equal to, this is a quadratic equation on the right-hand side. There's no e's, there's no cosines or sines, so we don't have to worry about that. We're just going to say that our particular solution also has to be a quadratic equation. So let's just make it to be a generic quadratic equation, a t squared plus bt plus c. We're going to do the same thing that we did in the last example. We're going to take the derivative of this thing. We're going to have to do it 3 times, though, and plug it all in. So the first derivative, we're going to get 2at plus b. Oops, that should be the first derivative here, sorry. Great. And then the second derivative, that's just going to give us 2a. And then the third derivative, that's going to be 0. Okay. Plugging all of this into here. So we can just write it out as is. It's going to be that d squared minus 1. Oh, sorry. We had it written differently, didn't we? Yeah, d squared minus 1 times d plus 1. That is going to be operating on what we think is the solution. I just realized that I interchanged x's and y's. Sorry. We're solving for function x, so that means that my homogeneous solution should be x of h, and down here my particular solution should be x of p. Change all of these to x's as well. All right, I'm just going to leave it. That's a p. Okay, great. I can't do it. I had to fix it. All right, so this is going to be plugging this operator onto my particular solution, x of p, the d squared minus 1 times d plus 1. So we'll multiply out this operator so we can actually do it a little bit better. So this is just foiling that operator with itself. We get d cubed plus d squared minus d minus 1 operating on our particular solution here. All right, so this is going to be that same thing, d cubed plus d squared minus d minus 1, operating on our particular solution, that a t squared plus bt plus c. But we've already figured out most of these derivatives, so we don't have to refigure them out. The third derivative is just 0 plus, now we're going to do the second derivative on that thing, which is 2a, minus, we're going to do the first derivative, 2at plus b, minus just the function itself, the at squared plus bt plus c. And this is all going to be equal to the right-hand side of this differential equation from up here, negative 2t minus t squared. All right, I'm going to dot, dot, dot here. Here you would just solve for the a, the b, and the c. A would come out to be negative 1, b would come out to be negative 4, c would come out to be negative 6. Not too hard to see that. This says that my particular solution, sorry, x of p, should be negative t squared minus 4t minus 6. Which means that the solution to just x is adding those two things together. The homogeneous solution from up top plus my particular solution. So minus t squared minus 4t minus 6. We did a lot of work, but this is just x. We still have to figure out what y is. Luckily, it's not too bad. So if I go back up to the original thing up here, we can solve for y and kind of get it by itself. Remember that there is another thing that we could do, is that we could kind of start over and do the elimination method again, but I'm not going to do that. So what I'm going to do is I want to try and isolate the y and get it just by itself. So from these original two equations, I'm going to subtract these two equations just to get the y by itself. So the first equation minus the second equation, that way these y primes cancel out. So hopefully you have it in your notes up there. If you subtract those two equations, you should end up with this. D squared minus d, that's operating on the value x, plus just the y by itself is going to be equal to negative 1 minus t squared. So the whole reason we're doing this is that we're trying to get the y as just a function of x. So now we're going to subtract this operator, d squared minus d operating on x over to the right-hand side, still have the negative 1 minus t squared here. Okay. Now we just plug it in, right? So we have our solution x here. We're going to have to take the second derivative and the first derivative of it to plug it in, but you just plug it in at this point. So now we're going to substitute the x from above. I'm going to dot this one as well because it's kind of obnoxious, but just know that y is going to come out to be this. So negative c2 e to the t minus 2c3 e to the negative t minus t squared minus 2t minus 3. So again, this is taking this x, taking the first derivative, that's going to be this negative d on the x, taking the second derivative, which is going to be the negative d squared on the x, then just plugging it in and combining like terms together. So once you have the x or the y, try to find an equation that only has the missing one by itself in terms of the other and then plug it in.